Okay, so it's already time and I'm going to start my today's session. Hope that others will join soon. Today I'm going to discuss a few problems on the topics that we have covered in our previous class. So I'm going to start with the problem and I'm going to explain the solution to you. Okay. So my first problem, and these are very small problems, and this type of problems you can encounter in online examinations, but you have to know how to deal with the problem, and that's why I'm going to show that to you. Let H be a normal subgroup. H be a normal subgroup of a group G, and H contains only two elements. H contains only two elements. Then we are supposed to prove. Then prove that H is a subset of ZG. I hope you can recall the definition of ZG. ZG is actually the center of the group, and the definition of ZG and the definition of normal subgroup will be used over here. Okay, so just to make sure that you recall the definition of the center of the group, I am going to write the definition of ZG besides this on the right side of the page. Center of the group, capital G, which is equal to all such elements of G such that that element commutes with other elements of the G also. Okay, so this is called the center of the group by definition. Now here in this particular problem, there is an important point that H contains only two elements. H contains only two elements. Now you see that if I have this group capital G, and in this group we have a subgroup capital H, then since capital G is a group, and if E is the identity of G, then I have already told you that in the current scenario, this identity element E will belong to the set capital H. The subgroup will contain the identity element. You already know that. Now here in this particular problem, it is mentioned that H contains only two elements. So what are the possibilities in this case? If H contains two elements, here is the possibility. That the set capital H, which is a subgroup, first of all, it has to be non-empty, as it is saying that H is having two elements, so obviously it is non-empty. H is definitely a subset of capital G, no problem. H is a subgroup of capital G, that is also given. And H contains two elements, that means one element must be the identity element of the group G, and another element which is non-identity element. So this is the form of H in this current scenario. Small a is another non-identity element of the group capital G, which is contained in H. This is the scenario. Okay. Now, in the previous class, we have already come across several equivalent statements for normal subgroups. We know that if H is a normal subgroup, of capital G, then AH is equal to HA for all A belonging to G. Or this statement is equivalent to the statement, or if you can write, since I'm considering the element A over here, so here I am writing small a. The element is actually being generalized by a. Do not think that this a and this a is similar. Okay, so I think for writing the definition, it would be better if I actually use some other notation, because otherwise you may think that this a is being used over here. I'm writing the definition here. So definition was like this, and the another definition, another form of the definition is as follows, that if capital H is the normal subgroup, then GHG inverse is equal to capital H. GHG inverse is equal to capital H. Now we want to show that H is the subset of the center of the group. And we know that if I want to show that capital A, the set capital A is the subset of another set capital B, then the process is we take an element from the set capital A and we want to show that this element also belongs to the set capital B, which is true for all X. Then only we can say then that A is a subset of B. So we are going to choose an element from the set capital H. Okay, and I'm trying to show that this element, this set, this element X is element of ZG also. Now, since H is a normal subgroup, if I write X belongs to H, then X belongs to GHG inverse. Why? Because I already know that if H is the normal subgroup, that then this happens. And if it is the case, this happens for all G belonging to capital G. Now, if this is the case, then we can write it as X is equal to GHG inverse. What does it mean? It means that the element X, which is the member of this set, can be written in the following form: for some H in capital H. Okay, now you see that this, when I'm writing for some H in capital H, and also I must write and for all G belonging to G. Okay, so whenever I'm writing that for some H in capital H, that means there is only one possibility. One possibility is this, another possibility is that. Okay, suppose this H is the identity element. This is my case one, where I'm considering that I'm choosing this for some H, where I'm writing for some H, this H I'm choosing to be the identity element. Then we can express my X in the form GEG inverse for where H is chosen to be the identity, which belongs to capital H. Okay, and this X then can be written as GG inverse, because you know that whenever a group element is multiplied by the identity, the element remains same, and in turn it gives you X equal to E. And we know that if X equal to E, it must belong to the center of the group also. Because why is it so? Because according to the property of the center of the group, it contains all such elements of the group G for which this holds. Now, E belongs to ZG because XE is equal to EX for all XE equal to EX, because it is written that this must be true for all G belonging to G, and therefore E is the element over. Oh, you can write here, in this case you can write for all X belong to X, for all X belong to G. If you are confused, if I don't want to make you confused, you don't think that this X and that X is same, so I can use another term, X prime, then you will not be confused. This is the definition what I'm writing over here. So I'm justifying the fact why the identity element must belong to the center of the group, because for all X prime belonging to G, X prime into E is equal to E into X prime. And it is happening because of the choice of H to be E. So we started with X belonging to H, and we ends up with X belonging to ZG, and therefore let us not write anything over here. Let us write that our observation only, that X belongs to H. If X belongs to H, then X belongs to ZG when X is equal to E. One possibility is done. This is one possibility that we have covered. Let us try to find out the second possibility, because we have to deal with only two possibilities. Okay, so I'm going to the next page. Let me save the chat, for instance. Okay. So in the next page, I'm writing that the case 2, where I'm assuming that now the element X that I'm choosing from the set H is not an identity element, Okay, and suppose my element X, and this implies that X not equal to E and X equal to the element A, because of I have written over here that H contains two elements, E and A. Okay. You can do one thing, one rectification that I can do over here, just to make sure that there should not be any notational ambiguity. You can write the element of H to be small h. Do not write A. Otherwise, there may be some trouble in understanding the element of the group, and especially the element of the subgroup. Let us call the element of the subgroup by the letter small h. Then it would be much easier for us to understand, to relate things. So I'm writing this element to be h, small h, denoted by small h. Now, if it is so, then as H belonging to capital H is not equal to E, this implies that H belongs to G, H, G inverse. And since H is the element of this set, then H is equal to, H can be expressed as the element of the form GH, G inverse, for all G belonging to capital G. Okay, and we can multiply both the sides by the element G of the group. So this gives me HG, and we can associate them together, and that gives us HG equal to GH. Okay, HG equal to GH for all G belonging to capital G. And this implies that H belonging to ZG, you have already guessed why is it so, because it is directly showing you that this result is true for all element G of capital G, and therefore H must be in the center of the group. So here also in case 2, we started with a non-identity element of H, and we have come to know that this element is also in the set ZG. By combining the two cases, for E, H belonging to H, we find that X belongs to H implies X belongs to ZG for all X belonging to H, and therefore H is subset of ZG, which proves your result. Now you may ask me one question, that why these proofs are actually not going to come in the examination. Okay, so you may ask me this question, that why, why do we need to do this problem? Why are you doing showing us this proof? Do not consider this to be a proof. Let us consider this to be a problem. Now, how can the online examination question can be set? I'm not writing anything on the board. I'm just saying, you just note it down. If someone asks me to set a question paper, online examination question paper, then I can select this particular problem and I can put the question in the following manner. Let H be a normal subgroup of a group G. Then H is the subset of the center of the group. Number one, if number one, H contains infinitely many elements, H contains identity element only, H is equal to G, and H contains only 2 elements. So these are the 4 options. Now you tell me that suppose this result you are actually trying, what we'll do, you will actually try to memorize this result. There are 1,000 results in group theory. How many results are you going to memorize? All the results are not the theorems. So that's why this type of problems have to be practiced, and you have to take the pain to deal with the problems in online examination also. That's why I'm doing this type of problem. I have already told you how a particular question can be set with respect to the given problem. In this respect, I am going to talk about another problem which is also very important, and the problem is as follows. I shall not consider this to be a theorem. I'm not going to consider anything now as a theorem. Let us consider this to be a problem. It is saying that prove that every subgroup of a commutative group is a normal subgroup. Every subgroup of a commutative group is a normal subgroup. What type of results you have learned so far? Every subgroup of a cyclic group is cyclic. Every group of cyclic or prime order is cyclic. Okay, this type of results you have learned. This is another result which says that every subgroup of a commutative group is a normal subgroup. Probably you are thinking that why this result is so important. You will get to see very soon why the result is very important, so important. First of all, I'm going to, since I'm considering this to be a problem, I'm going to prove the result first of all. Okay, so the proof is very simple. Suppose capital G is a group, okay, which is commutative, or you sometimes know that commutative, in place of the word commutative we can also write abelian. Now this implies that xy is equal to yx for all x y belonging to G. Okay, this is written because G is commutative. Now let H be the subgroup of the commutative group G, and obviously H is non-empty by definition of the subgroup. Now we select 2 elements H1, H2 belonging to H. These H1 and H2, when they are the elements, if we choose these 2 elements from H, actually we are choosing these elements from G. Because why? Because H1, H2, suppose this is my figure. If always try to remember the figure. So whenever H1 and H2 is selected from this particular section, actually we are selecting this from the entire sphere, okay, isn't it? So we can consider this H1, H to be the member of G, but we know that G is commutative, but the group G is commutative. The group G is commutative, and Hence we can write, hence we can write H, sorry, hence we can write H1 H2 is equal to H2 H1 in capital H. Now these HIs are actually arbitrary, your arbitrary choice. I am dealing with H1 and H2. That doesn't mean that it is not true for any other H, which others can select. Any other can work with H3 and H4. Another person can work with H1 and H10. So that's why I'm writing here that HI, the elements HIs are arbitrary. Let us now take an element from G and H in capital H. Let us choose this element in the following manner. Now, if I do so, this implies that AH belongs to A capital H by definition. So if I choose an element from G and if I choose an element from H, then their product will belong to the left coset. And not only this will also belong to the right coset, which is denoted by HA. Now, for A belonging to G and H belonging to capital H, which is in turn a subset of capital G, we see again that AH is equal to HA because capital G is commutative, because G is abelian, which is true for all H belonging to H and for all A belonging to G. Okay, and we know that whenever we write this kind of thing, that AH equal to HA for all H belonging to H and for all A belonging to G, this implies that AH equal to HA. And if AH equal to HA, then H is a normal subgroup of capital G. H is a normal subgroup of capital G, which proves our desired result. Now you see that. Just quickly take the snapshot of that. Okay, because I'm moving very fast because of you know that we have time constraints in the class. So we have very easily we can prove that every subgroup of a commutative group is a normal subgroup. Okay, so if I give you a commutative group and if I ask you whether it is a normal, if I choose a subgroup from there, and if I ask whether this subgroup can be considered to be a normal subgroup or not, then you will immediately reply to the question in affirmative. So I will now say to you that please do remember this result. It is very useful. This result is very useful, very important also. Okay. Now I'm going to show you a wonderful application of the given result which we have done just now. So I'm giving you a problem, and I'm going to show you how this result can be useful over here. Show that 12Z is a normal subgroup. 12Z is a normal subgroup of the group 3Z plus. Write Cayley table. Write Cayley table for the quotient or factor group 3Z slash 12Z. Very important problem. And remember one thing, I told you this particular scenario earlier, but again I'm trying to remind you, whenever I write that AH equal to HA, or whenever actually whenever I define AH, the left coset, and HA to be right coset. Okay, it is not a matter of these two things to be equal. I'm discussing right now. This notation I'm talking about, whenever we actually do write so, actually we are considering A star H. It is simply being written as AH. And here actually I'm considering H star A. So in between A and H, there is a composition. But whenever the composition star is plus the addition operation, then in place of A star H or AH, we simply write A plus H and H plus A. So with respect to the operation of addition, A plus H, this notation is actually used for left coset, and H plus A, this notation is actually used for right coset. Okay. Now, what about this question? Now carefully observe. What is Z? We know that Z is the set of integers. The set of integers. We can express Z in the following manner: 0, plus minus 1, plus minus 2, plus minus 3, and so on. What is 3Z? 3Z is the set of integers which are multiple of 3, So the elements of 3Z will be, 0, plus minus 3, plus minus 6, plus minus 9, and so on. Element of 12Z will be the set of integers which are multiple of 12. So these elements can be written as 0, plus minus 12, plus minus 24, plus minus 36, and so on. Okay, so we have these sets with us, and it is also a known fact that Z plus is a group, 3Z plus is a group. So this thing, and 3Z plus, why 3Z plus is a group? 3Z plus is a subgroup of Z plus. 3Z plus is actually the subgroup of Z plus. So we can easily check it. Now, how to show that 12Z is the normal subgroup of the group Z plus? So let us try to show it. We know that, and it is clear to observe from the definition, that 12Z, this set, is a subset of the set 3Z. Okay, and 3Z plus is a group, and also 12Z is definitely non-empty. Okay, therefore it is easy to observe that 12Z is a subgroup of 3Z with respect to the operation plus. But 3Z plus is a commutative group, and 12Z is the subgroup of the commutative group 3Z. Therefore, this implies from our earlier result, 12Z is the normal subgroup of 3Z. Okay, so you see, if you know the result, how easily you can find that this 12Z is a normal subgroup of 3Z. Okay, there is nothing to show in this particular case. So first part of the problem is done. Why 12Z is a normal subgroup of 3Z? Because 3Z is a group and it is commutative. Every subgroup of a commutative group is the normal subgroup. That's why we can easily write it. Now, the second part, let M belonging to 3Z. I am choosing an element M from 3Z. By division algorithm you have done in your school curriculum. By division algorithm, there exist two integers Q and R belonging to capital Z, such that this member M of 3Z can be expressed as 3Q plus R, where R will lie between 0 and 3. This is the statement of the division algorithm. Okay. Thus, M plus 3Z, if I write like this, M plus 3Z is actually equal to 3Q plus I'm going to design the quotient group 3Z/12Z. That is our objective. So I'm trying to do that actually. So no, I'm choosing the element not from 3Z. I'm going to choose the element from 12Z, because I have to make the quotient group with respect to 12Z. So I'm choosing element from 12Z, and by division algorithm there exist two integers Q and R, so that this can be written as M can be written as 12Q plus R, and R will lie between 0 and 12. That is the thing. R is lie between 0 and 12. Now M plus 12Z can be written as, this can be written as this M plus 12Z can be written as, in place of M you can put 12Q plus R plus 12Z, and you can separate the two things together, 12Z. In this manner you can write, and which is obviously, you can see that this is obviously can be written as 12Z, because there is no difference. Q is just a member. So 12Q will definitely be the member of 12Z. So entire thing can be written as R plus 12Z. The entire thing can be written as R plus 12Z. And so the quotient group 3Z, here the group is 3Z and the normal subgroup is 12Z. The quotient group 3Z/12Z is actually given by the following set. So what we get, see the range of R can take any value from 0, starting from 0, including 0 and less than 12. So what are the possibilities? First of all, we will write in place of R, we will put 0. So we'll write 0 plus 12Z. This is one element. Second element, this is one left coset. Second left coset is 1 plus 12Z, 2 plus 12Z, and in this manner we will go up to 11 plus 12Z. That's it. There will be nothing like 12 plus 12Z. Okay, so these are the elements of this quotient group. And the operation star, what is the operation of the quotient group? If you can recall from my previous class, that AH star BH is equal to AB H. So if I take the quotient group to be the left coset to be of this form, A plus H and B plus H, in this, with respect to this notation, this composition gives you A plus B H. Okay, now you can form your Kelly table very easily. Kelly table, to form Kelly table, we have to write it in this manner. We put the operation star over here. We put all the elements, 0 plus 4Z, 1 plus 4, not 4Z, 12Z, sorry, 0 plus 12Z, 1 plus 12Z, 2 plus 12z. All these things will be written over here. I'm not writing all the things. 11 plus 12z. And here also I'm going to put 0 plus 12z, 1 plus 12z, and in this manner 11 plus 12z. And what you can now do, 0 plus 12z, you can use this operation over here, a plus h star b plus h gives you a plus b star h. Here h is equal to 12z. Okay, so you can write it as 0 plus 0, 12z. You can write it as 1 plus 12z. And lastly, you can write it as 11 plus 12z, and so on. And if you write 11 plus, suppose I'm writing here 11, whenever we come across this 1 plus 11, 1 plus 11 plus 2, 1 plus 12z plus star 11 plus 12z, that will become 12 plus 12z, and the cycle will return. So in place of 12 plus 12z, we will write it as 0 plus 12z. So there will be cycle from 0 to 11, and it will move on running, keep on running. It will keep on cycling. So in this manner, you can fill up the following rest of the table. I do not have time for this particular session, so you try to fill up this table. Don't remember that 11 plus 11, you cannot write 22. Some elements from there will